So, welcome to this first video on mathematics for machine learning. This series is going to cover some material from a couple of different undergraduate math courses. We'll see some stuff from elementary statistics. We'll see some stuff from first two semesters of calculus and then some multivariable calculus, and we'll see some linear algebra. So, we're hitting a lot of the highlights of first 2 years of an undergraduate mathematics major. I'm going to try to apply very specifically to machine learning and how that mathematics is important in machine learning and try to give you an intuitive understanding of how mathematics works so that you can understand the machine learning better. So if you're taking AP statistics, a lot of this first section will probably be pretty familiar to you because AP statistics is a little more advanced than a typical first year elementary statistics course at an undergraduate level. So I want to just clarify the difference between data and statistics. Data is information that you are collecting about the things that you are studying, and then statistics is computational summaries that you make of the data you've collected. So the first topic I want to hit is types of data. Quantitative numerical data is stuff that's made up of numbers. So, if you have numbers like 1, 2, 3, it could be numbers that are decimals. It could be fractions. Qualitative categorical data is things that fall into categories. Sometimes numerical data can be categorical, for example, zip codes, because it doesn't really make sense to add zip codes. You're not going to apply arithmetic operations to it. Dog versus cat versus panda is a classic machine learning computer vision data set where you're trying to distinguish among dog, cat, panda, things like that. So anything where you're trying to place something in a category, then you're in categorical. Same thing with the digits data set. If you're trying to figure out if it's a 0, 1, 2, 3, that's going to be thought of as categorical data. This is going to help us understand what kind of machine learning we're going to be doing. Types of number systems. Discrete number systems are, for example, the whole numbers. And so here, the important piece is that they're separated by some distance. And so any discrete set of numbers has separation from one element to the next. Continuous are no separation. For example, the decimals. You can get as close to each other as you want. And it's a little more complicated than that, but that's going to be good enough for what we're doing. When you're doing machine learning, classification problems are ones where you're working on discrete sets. You're trying to fall into some category. So categorical data, if what you're trying to predict is categorical data, you are certainly doing a classification problem. If it's numerical but discrete, you're also doing a classification problem. If you have continuous predictions, you're trying to do continuous predictions where you're trying to just find some value in a range, then you're doing a regression problem. And so those are two very different kinds of machine learning with very different methodologies and goals. And so, we're certainly going to focus on classification in this course, and that's all we've done so far. We just want to be able to identify something as a classification problem. So when you have data, it's typically arranged in a rectangular sort of array where you've got rows are called individuals or records. For example, if in the digits data set, you've got the first picture, well, what is it? It's a 64 or 8 by 8, 64 pixel image. Maybe it's a picture of a 0. You've got 64 different pixel brightness intensities. So that's going to be row 0. And then in row 1, you've got another picture. Maybe it's a picture of a 6. And again, you've got 64 pixel brightness intensities. If you were to actually look at the data set, you would see something that looked like this, where you've got, so say in picture 0, if I'm going across the top row of pixels, maybe the first 3 have no writing at all in them. And then in the fourth one of this picture of a 0, you start to see the top left corner of the curve of the 0. If I'm looking at the picture of 6, maybe that was a little further left, and so we get just a little bit of trace in the third pixel, and then the fourth pixel is, the brightness level is pretty high, because again, if you remember from the digits data set, the brightnesses are all from 0 to 15, and you can keep going. You'll have 64 total columns of data across each one of them. You'll have this arranged in a large rectangle, so you have one row for each, in this case, each picture of a digit, and you'll have 64 columns, one for each pixel in that picture. So the rows are, in machine learning, they're typically called records, and the columns are called variables. In statistics, that's often individuals for the rows and observations for the columns. So just to match those two pieces of terminology. So here for types of graph, I just want to give you a couple of quick examples because these are things that you may decide to draw to make your life easier in understanding what the data set looks like. We'll take a look at more of this a couple of videos later in order to get a sense of scale on these, and these may be useful tools for you. There's a bit of a difference between a bar graph and a histogram, and I'm not going to get into it for this course, but the idea is you would, if you have categorical data, you're drawing a bar graph and you'd be just saying, counting up how many individuals, how many records fall into each category. And so you start by, you make this chart where you've got the category and the number of records. If you have numerical data, be it continuous or discrete, if it's discrete, you could choose to make each entry a category, and that can make sense. You can also just do ranges instead. These could be, for example, if you're looking at the California home price data set, these would be every $50,000 or every $25,000. You would break that range of prices up into chunks, and then you would just count how many houses fall in each of those chunks. So that's going to be true also for the line graph. And then the idea is you would have one spot for each category or range, and over here you would have the number of records, and then you can just draw bars. And if you want to make a line graph instead, you're just connecting up the points at the tops of the bars. Same idea, same visualization, and it gives you a sense of the spread of the data. Is it mostly on the small side? Is it mostly on the large side? Is it mostly in the middle? How many of them are close to the max? How many of them are close to the minimum? How many of them are close to the average? So it just gives you a sense of how the data is distributed within that variable. So scatter plots are really useful. It's a multivariable graph. So here you're looking at the distribution of a single variable when you're drawing the bar graph or the line graph. When you're doing a scatter plot, it's a multivariable. You'll have two different variables. And often when we draw a scatter plot in machine learning, we're going to look at one input variable. And so, for example, in the digits data set, that would be the intensity of one single pixel across all the different records, all the different objects that you're studying. And then typically you would look at the output variable, which is the thing you're trying to predict. And so if you are doing a classification problem, this is going to be discrete. You're only going to have certain locations and you're not going to have anything in between. And so your scatter plot is going to tend to look something like this, where all your points fall in rows. If you have a regression problem, these will be more scattered and you'll have a wider range of points to work with. You'll be able to fit this with a curve more easily and things like that. But for a classification problem in machine learning, this will typically, they'll just fall in rows. It can also make sense if you're looking at the relationship between two variables, two of the input variables, to put one input variable here on the bottom, and then a second input variable here along the y-axis. You get something more like this, where you've got a scatter of points. If you have two different continuous numerical variables, you'll have a point for each, 1 point for each record. So in statistics, it's pretty common to look at distributions of variables and try to draw conclusions about them. So first, we'll look at what's called the normal distribution. Normal is a very common word in common usage. We don't mean that in statistics. The word normal in statistics has a very specific meaning, and it means that you've matched this sort of bell curve. This could be a line graph, this could be a bar graph, but the overall shape of it is going to be a bell curve. And so again, we're looking at one variable. You've got your categories across the bottom, and then you've got your number of records in each category. For example, if you look at adults and you look at how tall they are, then if you specify a biological sex, it's easier because you tend to not have separate peaks for men and women. People whose biological sex is male tend to fall in this sort of shape where you have a fairly small number of very short people, you have a fairly small number of very tall people, and then a lot of people fall in the middle. There's an important idea here that's often associated with normal distributions, but it certainly can be computed for other data sets. How valuable this information is for a data set that's not normal can be questionable, but the center of a normal distribution should be the mean. What the center of a data set means is a complicated idea. Typically, we look at three different measures of that: the mean, the median, and the mode. They all agree in the case of a normal distribution. And so we use the mean, which is just an average. You add up all the entries and you divide by how many entries there are, and you get the mean. There's a measure of spread, which comes about here, which is called the standard deviation. And this distance from the mean to the right or the mean to the left line, either one of those distances is equal to 1 standard deviation. It is a measure where if you have a normal distribution, then about 1/3 of your data should fall into this section, and about 1/3 of your data should fall into this section, and the other 1/3 of the data should fall outside of that 1 standard deviation range away from the median. And if you go a second standard deviation out, so now we're 2 standard deviations out, then here to here, if I go from 2 standard deviations below the mean up to 2 standard deviations above the mean, then you should get about 95% of the data in that range if your data set is approximately normal. And if you go 3 standard deviations out, you should get about 99.6% of your data in that range within 3 standard deviations of the mean. Normal distributions have massive implications in statistics, and you use them a ton because they are sort of the natural place for data to end up under certain circumstances. And so you can use them to draw all sorts of conclusions. But you have to know that your data either fits it, or you have to work with your data by taking averages of subsets or something like that to force it into that category in order for these kinds of numbers to be useful. Next distribution would be a uniform distribution. And again, we're looking at a single variable distribution where we've got, sort of our categories. And again, these have to be sort of numerical categories where they're ordered naturally from one to the next. And you've got number of records coming up the vertical axis. And if you have a uniform distribution, then all your heights are the same, roughly. You don't actually expect the bars to be exact matches, but if they're all basically the same or close to the same, then you have a uniform distribution. That's all. So if you have 2 variables and you're looking at the relationship between 2 variables, these could, again, just as we looked at in the scatter plot, it could be the input variable and one input variable and the output variable. The other possibility is you could have 2 input variables. When you graph the 2 variables, if it's linear, then you should see a pattern in your scatter plot where you should be able to draw a line through it that reasonably well fits the data set and goes close to most of the points. You can have some less correlated data that's further from a line, but the overall trend, like something like this, would still be fairly linear because you've got sort of this empty area here and empty area here, and there's sort of a proportionality here. Anytime you have linear data, the thing that's most important about a linear relationship is that a linear relationship has a slope, and the slope is consistent from one part of the data set to another, or one part of the curve to another. So if you move over a certain amount in the x direction, you move up a certain amount in the y direction, that pairing, if I do the same distance in the x direction somewhere else, then I get the same amount of y change as well. And it doesn't have to be this way where this is an increasing set. It could also be decreasing where the line points downhill. That's fine. Again, if I move forward to the right in x, then I move down in y, but the relationship is the same. That if I move a certain amount in x, I move the same amount in y. It doesn't matter where in the data set I am. So, and that's the fundamental, most important idea of a linear data set, linear relationship. The next one is exponential. So if you have data where the amount of increase changes from one end to the other, you get some sort of curved data set. And so an exponential curve is fairly common. You've got sort of 2 versions of an exponential graph. The first one would be exponential growth. For a random example, spread of a virus among a population, if it's uncontrolled, it starts out fairly slowly, but then becomes much more rapid. And so a certain amount of increase here in x results in a fairly small increase in y, but over here, a small increase in x results in a very large increase in y. And so that's exponential growth. Other things would be, for example, interest accumulating on an account or growth of a stock portfolio. If the market's going up, you would expect exponential growth because the amount of growth is dependent on the base amount that you have in the account or in the population or whatever. And so the more that accumulates, it feeds on itself and it accumulates more and more and more. And so that's how exponential growth looks like. You can also have exponential decay. Classic example, of course, is radioactive decay. And so what you're looking at is the mirror image of the left-hand graph, where you're looking at sort of the downhill side of it. An exponential decay graph would look like that. And if I put these 2 graphs together, flipping one of of them across the y-axis, then they would form a single exponential curve. But in data, you're typically only looking at forward movement in time to some extent. And so you typically have a one unidirectional data set. And so you don't always worry about both directions. And so the growth is sort of separate from the decay in a lot of cases because we're moving forward in time in some sense, or forward in something. We're not unbounded in both directions. And so with exponential decay, the further along you go, the less change there is, because the less there is to decay. Radioactive decay, where every, say, if it's got a half-life of 1 day, every day there's half as much as there was. So if you started out with 16 grams of something, the next day you have 8 grams of that same isotope, and then the next day you have 4, the next day you have 2, and so you lose less each day, because even though it's still half, the actual gram amount is changing each day and getting less and less. Logarithmic is the inverse of this, where if you flip the exponential growth curve across the line y equals x instead, then you're looking at a logarithmic growth. And usually when you hear somebody in the media say it's growing logarithmically, they usually actually mean exponentially. They're often wrong when they say this. If you have a property of a population that becomes rarer the larger it gets, so an example of that might be total wealth of a family, total household wealth. You have lots of people who have low levels of wealth up to zero, less than zero, and then 0 to maybe 50,000 or whatever, and you break it up into those ranges. But as you go higher, you get fewer and fewer and fewer people who get into those categories. The vertical axis here, where total population less than or equal to this amount, then that's going to grow logarithmically. Same thing with populations of cities. There are lots and lots of cities that are up to 100,000 people, say, but when you get up into the millions of people per city, they get to be fewer and fewer of them. And so the number of cities that you're adding to the total who have less than or equal to that population amount is increasing logarithmically. Another one that we probably won't do much with, but I felt like I should mention it, is sinusoidal. That means it's a combination of sines and cosines of different periods. So anytime you have data, so like if I'm looking at a line chart here where it's repeating roughly from one section to the next, that's going to be sinusoidal. You're looking for this regular repetition or approximate repetition of patterns. Anytime you have a regular repetition of a pattern, then you have some sort of sinusoidal effect going on. This is common in what are called time series, where, for example, if you're looking at labor data over a period of years, then they typically follow some sort of seasonal pattern. And so you have this regular repetition from one year to the next, where it goes up during the summer for migrant labor, goes up in retail and the Christmas season, and so on. You get this regular repetition pattern of data, and that repetition, that periodicity, periodic nature, is going to be modeled by a sinusoidal function, some sort of combination of sines and cosines. I'm going to use the word dimension quite a bit later, and I just wanted to be clear about this because I'm going to be using it in a way that's maybe not so close to the way that is sort of common and familiar. People often ask, well, what's a fourth dimension? And we all know that Einstein answered time in 1905 in the special theory of relativity. This is the correct answer for the space and the universe that we live in. But this is not what I mean when I say I'm looking at the fourth dimension of this data set. So in the case of a data set, in case of machine learning, so we've got this, if we have a data set sort of set up in our classic rectangular pattern, this first variable is considered the first dimension of the data set. The second column here, the second variable, variable 1, is considered the second dimension of this data set. This is the third dimension of this data set. This is the fourth dimension of this data set. And so the fourth dimension is whatever the heck variable number 3 is, whatever your fourth variable is. And so whatever it is that you're measuring about your data set is the collection of dimensions that you have. For example, in the digits data set, you've got a 64-dimensional data set. You have 64 pixels. The value in each pixel has been tracked. They're independent of, or not entirely independent of each other, but somewhat independent of each other. And that information is the information that you've recorded and you're studying in your data set. And so you have a 64-dimensional data set. This is an important idea. It's going to come back to us in later when we start to think about how we actually build these models. But really, a dimension is just a separate measurement you can take about your data set. And so that allows us to get, and we're certainly going to get into very high dimensional data sets very easily, such as in the digits data set, we'll get into 64-dimensional data. We've already done that. That's an important idea in the study of machine learning, that we're going to be thinking about dimensions in this sense, not in the sense of space and time.